plane wave, which is it's really a high-end telescope in terms of what it's for. It's super corrected, so that you have very little distortion of any kind in it. And we had enough left over to buy a really good Dobsonian, which is they would say it's the most scope for the least money. It's basically a Newtonian telescope on a Dobsonian mount, which is a kind of a swivel thing. And it's the same kind of telescope that Isaac Newton designed years and years ago. So it has a bigger mirror than the plane wave. So it actually gathers more light. And that's one of the things I'll be talking about tonight, because we've got pictures this time. This is the first time we've got pictures from both telescopes. Because even though they both track, they're called go-to scopes. You know, you orient them and get them aligned properly, and then they will track. They should track all night long, but the Dobsonian is not as precise. And when people look through it, they won't see any drift. But if you start taking time exposures of, say 30 seconds, you'll see the stars smearing out, and that doesn't look good. So we weren't able to get pictures, but we've been working on it. And particularly with John's expertise, which I'll talk about in a little bit, we really got some amazing pictures with it, because it has a 16-inch mirror, whereas the plane wave only has a 12.5-inch. So the Dobsonian scope will actually gather over 60% more light. So you can see, so looking at dimmer things, they're better through that. And like I said, particularly when you get them in the center of the scope. And there's not much distortion, but a little bit on the outside. So we got some, after practicing over the last year, we finally got, we were able to get some good pictures with the Dobsonian. So I want to show you those tonight in the thing. So I guess we'll go back to the first slide, but I want to say a little bit about, here's our team. Here I am, and this is Donnie Bunch, and here's John Phelps. Now, you know, I insist that the angle of this picture made me look fatter than I really am. At least that's going to be my story, and I'm sticking to it. But at any rate, this was taken last summer in July when we were up for session back then. We all three have been working together for the last 2 years. And I'm really sorry to say that John Phelps is going to be leaving us. He's moving to, some of you were hearing about it earlier on about selling his house. He's moving to Las Vegas. So it's going to make it, we can't pick up the phone and say, hey, John, can you come down tomorrow night or next week? So it'll be some time before we can do that. John is the camera expert. You know, Donnie and I have been operating the two scopes. I've usually operated the plane wave scope, and Donnie usually operates the Dobsonian. So, but when we made a decision at the very beginning to use DSLR cameras to take all our pictures. Now, the reason we did that is because, well, first place, John had done a little workshop on nightscape photography using DSLR cameras at one of our U-Bar Star parties, one of the Western things we do every summer. Well, a lot of people have these cameras, and the sensors are getting better and better every year, so you can get some pretty good shots. So we said, okay, let's just go with that. We'll use that. We'll try to teach people how to use their cameras, and we'll do some other things. So we started, like I said, 2 years ago, doing just that. And John has given us the expertise with the cameras. I mean, I knew how to hook the camera up to the telescope, but you know, like I was telling Robin earlier, for the most part with my camera, all I do is set it on automatic and go. But when you take these pictures, everything's got to be manual, and so the fine tuning requires a good bit of knowledge. Hopefully, John has taught Donnie and I enough that we can limp along without him, but we're certainly going to miss it, because he has been just great to work with, very patient. He doesn't mind telling us something, because, you know, sometimes it would be 2 months before we'd get back up there. And he's got to tell us the same thing all over again. But, you know, we finally figured out we should write a few things down. Anyway, we have. So here's our team. And let's go to the next slide. All right, what I'm going to do tonight is I'm grouping these things. We've got more slides than I have in the past, I've used in the past. So I've grouped them together by kinds of things. In the very beginning, I wanted to do a group of what's called nightscape photography. I had mentioned that, but those are shots of the sky that you take without using a telescope. You just use a camera on a tripod, and you know, you may have a telephoto lens, but more often you use a wide angle lens. And so John is a master at this stuff. This is a shot John took probably, I'm not sure exactly when he took it, but he entered a contest and placed. And some of you have been to U-Bar, you're familiar with our iconic windmill. Well, John just got, and this is this looking southeast. There's Jupiter, here's the Milky Way. And he took a red flashlight and shined it on the windmill. Because if he hadn't done that, that's called light painting. It's more than just a nightscape shot. It's got light painting too, because he shined a flashlight on this. So it came up with a really cool picture. Okay, Robert, let's go to the next one. All right, you remember this last summer, we had the comet Neowise there. We took several pictures of that. I just decided to show them again because this is again another example of nightscape photography. John actually took this from his backyard. It's such a good one that he got there, so I wanted to put it in there, but it shows you what you can do with just a camera and a tripod. This was taken shortly before our session on July the 23rd. So I'm not sure whether that was the 21st or what, but anyway, John took this picture. Let's move to the next one. Here we are at U-bar-U, and we continue. This was done on the 23rd of July. There's Comet Neowise again. And here we've got light painting with a green laser. Now that's Donnie Bunch down here in the corner. So Donnie took the laser and was shining it on both sides of it. You're doing a time exposure, so we were able to kind of frame the comet with that. So it's kind of a pretty cool picture. And you all remember what Neowise is? You know, it's named after the satellite Neowise because they used to name comets after people because the person that discovered them. Well, this turned out a satellite discovered it, so it got named after the satellite Neowise, which is a big long acronym, stands for Near Earth Object Wide Range. Let's see, I forget the last part there, but this is this System Explorer or something like that. But anyway, that's one of the others. I got one more shot I want to show you. We'd go to the next one. There we go. We were fooling around with this in December. John has a drone. He put a red light on it. So this was a time exposure where the drone was zipping all around. And John was looking at it and he said, we can tell him this was a UFO over U-bar-U. And we decided we probably would have a hard time selling that. But anyway, it's just pretty cool because he just had it zip back and forth and the red light, picked up the different patterns you see here. There's the observatory, and this is a radio tower in the distance there. Of course, that's the night sky. All right, and that's the last of that group. Now, oh, I'm sorry, there was one more. I'm going to show you this photograph later because this was part of the series we did on the conjunction of Jupiter and Saturn. That's what they are here. I'll do this photograph again. But John took it, added the Christmas star to it and a Merry Christmas and made a Christmas card for the board. So it was a big hit. And in fact, we may even make some Christmas cards with it next year and send them out. But it was a really cool thing. Now, I want to move over to a group of what we call open star clusters. And this is exciting for a couple of reasons. This was taken with the Dobsonian telescope. Now, like I said, in the past, when we tried to do something like this, we got smeary stars. Well, playing around with the cameras, and I had to go back and look at the setting. Last time we tried to do this, we had like 30 seconds, and the Dob really was tracking not as well as it normally does. So they were smeared all over the place. Well, I went back and looked at the specs on this photograph, and this was only a 4-second exposure with the ISO cranked way up, 12,800. So as John tells us, it's kind of a dance. If you want to make the camera more sensitive, you increase the ISO, but you also get more noise typically. Well, this doesn't have much noise at all, and that's with John's very fine mirrorless Sony camera, the what's 7M3, I believe. But anyway, it's a really cool picture. So now go back to what it is. These open star clusters are all within our galaxy, and they'll have anywhere from a few dozen stars to a few hundred. This particular one, this is in the constellation of Riga, which is the Charioteer. And I've mentioned this to other people in the past. When you look at the constellation, I'm hard pressed to figure out how you see a Charioteer in there. But someone did in the past and made it up there. But it's very, very rich in terms of star clusters. You've got 3 beautiful open star clusters in there. But so I want to show you those 3 that we were able to photograph and then compare them to a globular cluster and then some other kind of so-called nebulas. Anyway, this was done on that December night we were there. We were there mainly to try to photograph the conjunction of Jupiter and Saturn. but you know, that turned out to be less than satisfactory. But we got some really great other pictures. Anyway, here is the first of the three. There, by the way, this is M36. You've got three M36, M37, M38. Those are the Messier numbers. I think we've mentioned this before, but in case you all may have forgotten, Messier was a French astronomer, and he was very interested in finding comets. So he when he was out studying the sky, he made a catalog of all these things that were not comets. He called them nebulas. Of course, he didn't have the kind of telescopes we've got now. And now that his list is more useful with what these things weren't, they weren't comets, what they are, and instead of the fact that they weren't comets. This was the first of the three he noticed in Auriga. So let's move to the next one. I'll show you. Oh, wait a minute. I'm sorry. Yeah, this was what happened. That was a single shot you saw there of M36, the open cluster. We took several photographs. What John did was to stack these and then do a little bit of enhancement. And so you get a really startling photograph here. This is the cluster here. All these other stars in here are background stars. It didn't show up until you had the longer time exposure, but it's really a cool photograph. Okay, let's go to M37. M37 is, you'll see a lot of blue stars. Actually, this cluster has more stars according to the books than M36. You'll notice they're very blue. The blue stars are younger stars, and this one has, I think, a few hundred stars in it. And the width of this thing is about 20 to 25 light years across. That seems like a lot. The distance to this cluster is some 4,500 light years. So it's pretty far out there for even an open cluster. But the thing about the young blue stars is when the stars are born, they tend to be blue. As they get older, they get more red. And then, of course, the other things happen to them. But you see all these a lot of blue stars in this thing, which tells you it's not that terribly old. Okay, now let's look at M38. M38 is the last of those three clusters. All of these clusters, these Auriga clusters, are within 4,000 to 4,500 light years away. And like I said, I think this one has a couple of hundred stars in it. It's very similar to the others. Notice you'll see most of these stars are blue, and a few little orange ones here, so they're a little bit older. These open clusters will eventually spread out. They'll drift apart, so you won't see that anymore. So what I wanted to do now is show you something that's a little bit closer. Let's go to the next slide. This is still a double cluster. This is pretty far out there too. It's around 7,500 light years away. We took this with the plane wave. I'm trying to think when I actually took it. This was back, I think, in the summer. I believe it was, yeah, back in July. I wanted to show you one more example. This was one cluster here and another cluster there. One of the things about the plane wave is that it has a higher focal ratio. So the field of vision is not as wide as the Dobsonian. The Dobsonian is like an somewhere between an F5 and F6. The plane wave is an F8. So its field of view is not nearly as wide. So I would like to have been able to get a little bigger. So it's hard to get an idea of these two clusters all together. But anyway, we were playing around with it. You got a pretty good picture of one of them down here. Like I said, this is about 7,500 light years away, and the two clusters actually have a couple of hundred stars each. But okay, well, now I want to move to the next one, which is this is what's really impressive. This is the Pleiades. The Pleiades is the brightest open cluster that you will see in the night sky, and it's often referred to as the Seven Sisters, because the seven bright stars that are in the cluster. It's about 400 light years away. So it's 10 times closer than the ones we just looked at. And it has a couple hundred stars in it. Of course, you don't see all of them. And when you look at, when you say, where are the Seven Sisters? Well, here we got four sisters. It turns out that even the Dob, I tried to take a photograph with the plane wave, and I got one sister. So with the Dob, we were able to get four of them. And here are the four bright stars here. There are three more outside of this range here. The Pleiades actually looks better through a pair of binoculars because you can see the whole thing. And it's about 30 light years across, and it's about, like I said, about 400 light years away. So you can actually see it as a kind of a fuzzy patch with your naked eye. Easily see it up at U-bar U. So here it is. It's called the Pleiades. And we took that on the same night of December the 17th. Again, this was with the Dobsonian and with John's camera. All right, this is an enhancement. We took that, what you just saw was a single shot. We took several, so John put them together, worked on the color a little bit, and so you got a gorgeous looking picture. You notice that the four bright stars that are referred to as the sisters are, it's beginning to smear out because they're overexposed. But still, the other stars, the smaller ones, are pretty round. So we don't see much movement in there, even with the stacking of different pictures. All right, I want to go now. I want to compare those with a globular cluster. We took this picture back in the summer with one of my cameras. It was a Canon EOS M77, which is kind of like the top of the line of the Rebel series. There's a new, they don't make that one anymore. It's an M80, but nonetheless, this was a stack of 3 photographs we took. But a globular cluster, all the globular clusters are outside of our main galaxy. They're in the halo of the galaxy. So they're like little satellite objects. So where those others were, anywhere the Pleiades was 400 light years away, the ones I showed you in Auriga was 4,000, even the double cluster was 7,500. This thing's 25,000 light years away. And it's about, it's about 100 light years across, but it's composed of hundreds of thousands of stars, possibly as many as 1 million. So yes, it may be 3 or 4 times as wide as those open clusters, but it's got 2 orders of magnitude more stars. So I mean, they're really densely packed together. And these globular clusters are very, very old. They are at least 11 billion years old. So when astronomers start studying things about it related to the age of the universe, and they tend to look at what's going on with these globulars as much as they can. Anyway, this one, and M13, by the way, is in the constellation Hercules. That's mainly a summer constellation, but it's the brightest globular cluster that we can see in the northern hemisphere. It's the 3rd brightest overall in the whole sky. The very brightest is down in it's called Omega Centauri, which they used to think was a star. It was so bright. You can see it with a naked eye, but we only can see it for a short time in the summer, very, very low in the horizon. We've never gotten a picture of it yet. When it's been high enough to take a picture of, it's been cloudy or we just missed it. So anyway, that's pretty cool. Now we'll look at some other, amongst the things that Messier had labeled with his M numbers. He called a lot of these things just nebulas. Well, some of these nebulas turned out to be galaxies. And so here you have, this is M31, the Andromeda galaxy. Now we talked about the globular clusters being like 25,000 light years away. This is the nearest galaxy to us, and it's over 2 million light years away. And its structure is very, very similar to our Milky Way galaxy. It's actually wider and larger in terms of area, but they think the mass is pretty close to the same. So we might be a little more dense than the Andromeda galaxy, but they're similar type, both called, it's called a barred spiral. Here you can begin to see some of the spiral nature of this. Now, this was taken, and I had my notes, I made a mistake. I said we took it with my Canon Canon EOS RF, but RP, excuse me. But this was actually taken with John's Sony. And this was 30-second exposure. You see the stars are nice and sharp pinpoints. So there was absolutely no drift in this thing at all. We've taken some pictures with using the plane wave of the galaxy that went up to as much as 4 minutes, and we didn't get any drift. But this was the one that we took, in that September session. All right, now let me show you something. Now, here is the same galaxy, was taken with the Dob. And you'll notice here, did you notice the difference when you saw the picture that I had to show you just a moment ago? The galaxy was laying this way. And now you see it that way. Well, it turns out that images when that plane wave are reversed left and right. They're okay up in terms of up and down, but left and right are reversed when in the way the images are formed. So it's kind of cool. Up in this corner here, you have another galaxy. That's M32. So I guess that's pretty much all we want to say about that. Let's go to the next. This was really cool. This is called the Ring Nebula. It is a planetary nebula, and it's created when a star sheds its outer layers of gas. It begins to cool off, starts kind of collapsing down, and then all of a sudden there's an explosion and it blows off a layer of gas. And what's left is a dim, smaller star, dim, more dense star in the center. You can probably make it out right here in the center of this ring. Can you see that? Is that visible to most of you right in here in the center? There's a little, it's very, very dim. This thing is somewhere between 1,000 and 5,000 light years away. They're really, usually they're better about measuring how far away these things are, but I couldn't find a good definition of just about how far it is. Anyway, this was taken again with John's Sony camera, and it is, like I said, it's at least 1,000 light years away. It may be 5,000 away. Now, I guess that's another. Oh, now this is another planetary nebula. It turns out this was also taken the same night. I'm saying that. Well, I got a different date on there. Maybe that's why it's not as sharp. What happens on a dumbbell nebula? This thing is 1,000 light years away. If a star goes through that process of shedding layers of gas twice, it turns out it creates two lobes. So you've got a lobe here, and you've got a lobe here, and there, I'm pretty sure that's the star. But here you go, and there you go, and you even have this dimmer, longer thing bubble around the whole thing. But it actually makes two different lobes, and apparently this is not the only example of that. But this is M27. This is one of the ones that Mercier found, and it's kind of a cool shot. I'm wondering, yeah, I guess that you see that the stars are smeared out a little bit on this one, as opposed to the one we had in the Ring Nebula. Can you bounce back to the Ring Nebula for a second? Or you see how sharp the points are here? When we go back, let's go back to the other one. A little bit longer exposure, but you begin to see a little bit of drift. But still a pretty impressive picture. Okie doke. Now, the third type of gaseous nebula that I want to show you, or another nebula, is this is the Great Nebula of Orion, M42. Now, it's different from some of these others in that this is basically a star factory. If you look at Orion, the constellation of Orion, which is one of the constellations that you can actually see, well, that looks like a person. You can see the hunter. This is down in the sword. There's the sword right there. And this thing is about 20 light years across in terms of what you see. And the distance to it is maybe 1,500 light years away. But the distance across here is about 20 light years. It turns out that this actual halo of gas really goes out 100 light years. It's cooler, but it doesn't glow. Now, what's going on here is that gravity is causing the gas to condense into little globs. The little globs get bigger and bigger, and they become stars. So essentially, this type of a gaseous nebula is basically a star factory. When you saw those open clusters, the stars are already they've already been born. They're there. It's not making new stars. This one is making new stars, and it's pretty cool. Now, I've showed you this picture because we took this right at the beginning when we were doing this stuff. This was last January of 2019. So a little over a year ago, we took this thing. But I want to show you something here. Actually, 2 years ago. Let's go to the next shot. It's the same thing, but here we go again with a better camera. This is the Orion Nebula that we took in December this past December the 17th. So we really got some sharp. Look how sharp the stars are. Okay, John, of course, did a little bit of work on the color there, I think, but it's a beautiful shot. We had several of them, but I had to include this. Okay. Now the next group is planets. All right, I'm going to show you several planets. This is Mars. It's the first time we've shown Mars. It turned out that Mars was an elusive thing to photograph. We went up there multiple times. In fact, John and I stayed all night long on the July the 27th because we were going to get up at 4 o'clock and take pictures of it. Well, that was a good idea, except the clouds rolled in at 4 o'clock, so we couldn't photograph it. And then we tried it again later. The next time in September, we had trouble with it. But what I wanted to do with all of these planets is to catch them at opposition. Now, opposition is when the planets will be the closest to the Earth. It's when they are on the exact opposite side of the Earth from the sun. So that's when the orbit of the planet lines up, it's closest to us. The planets are the closest for that year. It's not the same every year. So Mars on some opposition gets its closest 35 million miles. Excuse me, I'm saying light years too much. Mars at its closest approach to us is about 35 million miles away. This time it was around 39 million, which is still pretty doggone close in terms of of astronomical objects. But we were able to get a pretty good picture of it. Notice you can see the markings on it, the dark shaded things here. You also can see the polar cap. One of the right down here, this is a polar cap. See the white? So that was the best we were able to do. Now, what I would like to do in the future, and in fact, I've ordered this, it just hasn't come yet. When we attach the cameras to the telescopes, the magnification is roughly about 50. Now, normally when you figure out the magnification when you use an eyepiece, you take the focal length of the eyepiece and divide that into the focal length of the telescope, and that tells you what kind of magnification you're going to get. Well, it turns out that if the camera, it's a little bit different than that, but it's roughly about 50. So when you attach the camera to the telescope, you need a thing called a T adapter. And the T adapter, you can get them that have magnifiers in them. There's the most common thing is called a Barlow. But Teleview is one of the companies that makes really expensive stuff. They make one that they just call it an image enhancer. They don't want to call, because it's not really a Barlow. It's got, I forget what the design is, but it's pretty fancy. I ordered one that would give us, when we took this, we were using one that we had ordered. It gave us twice the magnification power. This is about 100 power. I ordered one that's a 4 power, but it has been on back order since the end of November. I'd hoped to have it for the December session. We didn't get it. But anyway, this is still a pretty good picture. And if when Mars was pretty close to opposition, like I said, we took this thing on the 11th of October. It was in opposition, exactly in opposition on the 13th. So we were really close to it. Okay, now let's go to I think Jupiter's next. Here's Jupiter. When Jupiter was in opposition this year, and this one was taken back in July, it reached opposition around the 14th of July. Well, that was still pretty close because its orbit is wider, of course, than Mars. So the difference of 4 or 5 days there didn't make as much difference as it would if that was many days with Mars, because it's like I said, its orbit is tighter than that, and it moves further along the length and it'll say a week. But this is very close to opposition. It was around 390 million miles away. Well, Jupiter is 88,000 miles in diameter. So that means it's about 11 times the diameter of the Earth. And it's closer to 20 times the diameter of Mars. So when you take 390 million as compared to the 39 million, it's 10 times further away, but it's also more than 10 times the diameter. So it looks bigger than Mars did. Some of the features that you can see here, these are 3 of the 4 Galilean moons of Jupiter. This is Callisto, it's the furthest out. This is Ganymede, that's Europa, and Io was behind the planet. One of the you see the nice bands we have here? Well, also there is the red spot. You've heard it, it's kind of orange, but that's the giant red spot right there. So we got a pretty good picture. Anyway, that was taken. I wanted to show you this because when we try to do the photographs that we took on the 17th of December, when we try to photograph the conjunction, you will see that it's not nearly as sharp as this. Okay, now let's go to Saturn. Here's Saturn. Again, that was taken on the 23rd. Saturn and Jupiter were in opposition pretty close together because that's why there was also one reason The conjunction was so close. But anyway, I think that Saturn was in opposition just a few days after Jupiter. So for all practical purposes, it was in opposition. The distance to Saturn here was something over 700, I forget how many, 700 some odd million miles away. So it's not quite the diameter of Jupiter. It's around 75 or 77,000 miles in diameter. And of course, it's further away, so it's not as big. But this is a pretty good picture we got, because if you can see the separation with the two major rings here, that's known as the Cassini ring, the Cassini separation, excuse me. Cassini was an Italian astronomer who first discovered that separation of those rings. He was after Galileo, but he had a better telescope. And so that's what we have there. And then now, I'm going to start with a series of photographs that we did trying to show you the conjunction. You've all heard about how close that, a conjunction is just the apparent position of two planets as viewed from the Earth. So Jupiter and Saturn are millions or hundreds of millions of miles apart in the sky. But what happened is that each year that they come around, and there's a period of time when they are closest to us, which they appear to closest to us. It turns out that in 2020, the conjunction of Jupiter and Mars it got as close as actually at one point it was a little bit less than 1/10 of a degree in the sky. Apparently less than 1/10 of a degree. Now, why is that? Well, a full moon is about 1/2 a degree in the sky. So when they were the closest together, and they're apparently the closest, they looked about 1/5 of the diameter of a moon when you look up. And actually, at one point, they were actually 6/600ths, but that happened during the daytime. You didn't really see that. Anyway, this photograph was taken in October, and you can begin to see that they're still fairly close together. Now, that's several degrees apart right here. But that's the first one we got. This is the photograph that John had used to put the Christmas star and the Merry Christmas on the top. But this is the same photograph. I want to kind of get you an idea of where they were. Of course, this is looking southeast. There's the Milky Way. He was behind the observatory. Roof, of course, is open. And there that shot is. Okay, now let's go to the next one. All right, now this was actually taken on the night of the 17th. The conjunction actually occurred on the 21st. So why were we taking pictures on the 17th? Well, turns out that was a good night for us to get up there. It was also a very good night weather-wise. And so we decided we'd get close, and if we could have gotten good pictures, what our goal was to be able to get one photograph of the two planets in the same shot, through the telescope. Really look cool, where you got Jupiter here and Saturn there, and with all the same thing. Well, what this is a nightscape shot that John took. And there was a crescent moon that night. So here it is. And it's 3 degrees from here to here. Now, the two planets were about 4/10 of a degree apart. That's still less than what a full moon would look like. So if everything had worked right for us, we would have been able to get both of those planets in the same single shot. Notice that if you look at the moon, and this was time exposure, so even though it's a crescent moon, we can see the rest, there's enough light to show the rest of it. Look at that, that's about 1/2 a degree, which is more than the distance between the two planets right here. Is that clear? And of course, that was with John with his Sony camera. Now let's go to the next shot. Okay, this was about this is about the best we were able to do. It turns out that that although the line of sight was very good, and your eyes are pretty miraculous. And if you looked at a telescope, you'd have been able to see the two planets pretty clearly. But the magnitude of Jupiter was so much brighter than Saturn. Jupiter was like magnitude -2.4 or something. It was brighter than -2. Saturn was about 0.6. So it had about, and these magnitudes are logarithmic in notion. So Jupiter was so much brighter than Saturn was. And when you try to take a picture, anything to get detail on Jupiter, you couldn't see Saturn. Anything to get detail on Saturn, Jupiter was just a blinding dot over here. So this is kind of a compromise. And the other thing that occurred here is that as you were taking the photograph, this was like shining a flashlight toward it. It was a bright light in the field. So to be able to get the picture that we had imagined, where you'd have this nice Jupiter with its bands and its moons, and then you'd see Saturn with its ring over here in one single shot. Basically, the way you have to do that, you have to use multiple shots where you use and then put them together. Do some photoshopping, do them together. And really, you need a more sensitive camera than we had. Some of you know Bruce Barton, who's got his own observatory, and Bruce did that. He actually used a specialty camera, took the photographs, and then pasted them back together. So it really wasn't a single shot, but it was still, it showed you what they would look like, and it came up with a very excellent looking photograph. All right. Now that was on the 17th of December. Let me show you the next one. Here, this is the same deal, but on the 19th. I took this from my backyard. I'd learned enough from John to be able to operate my own. I have a little observatory in the backyard, but the telescope I have is not as big or quite as good as the plane wave. But still, I was able to get this shot here, and they're only about 0.2 of a degree apart. So this is about half the distance of the other one that you may see. I think it was a little over, but certainly just barely more than 0.2, and that was good. But you know, like I said, I had the same problem. I took several photographs, and that's about as good as I could do. You might think you can see the rings a little bit here on Saturn, but you really can't see any markings on Jupiter. So, and I had dimmed it down so you don't see much of it. You can't really make out the moons. Okay, now let's go. All right, this is the end of the show of what we want to talk about tonight. This brings us back to U-bar-U. Now, John got up early and did a nightscape shot from over the fire circle with, here's Orion in the background. That's the belt. You know, here's the sword. That's the star of Rigel. And I wish we had the whole thing in there, but you get enough of it to know what it is. So it's Orion. Very good shot. And it's kind of a fitting way to end the year for what we've been doing all year long. Like I said, we owe a great thanks to John for all the good advice, photography, and everything else he's done for us up there. And we wish him well on his way to Las Vegas. All right, now we can go to a little question and answer period if you